Welcome to my 33rd tutoring session in A-level chemistry. In this video, I'll give a detailed explanation about factors affecting hydrogen bonding and its strength. Please take a moment to watch my previous video on the topic Principles of Hydrogen Bonding. My previous video will provide you with a better understanding of this video content. Link to the video is given in the description below. Please do watch the video. Don't forget to subscribe my channel, share, like, comment, and watch the full video. Now here's the figure explaining hydrogen bonding. And remembering this figure will make it easier to recall the factors affecting the strength of hydrogen bonding. So here are the list of factors affecting the strength of hydrogen bonding. Electronegativity of donor and acceptor atom, polarity of the molecule, size of the electronegative acceptor atom, extensiveness, where you find hydrogen bonding in networks, and environmental factors like temperature and solvent effects. So let me begin with the first factor, electronegativity of donor and acceptor. Before I get on with the explanation, I would like to share some important details with my viewers regarding the hydrogen bonding. And this will definitely help the viewers in understanding the factors affecting hydrogen bonding in a simple and lucid manner. So what you see here is polar covalent bond formation between hydrogen and fluorine atom. Hydrogen atom contains only one valence electron, and the only one valence electron of hydrogen atom where it is covalently bonded to the fluorine atom, the outcome is that the proton of hydrogen is completely exposed. And once the proton of hydrogen is completely exposed, there is a strong attraction of the completely de-shielded positively charged proton towards lone pair of electrons on the negatively charged acceptor atom, which acts as a Lewis base. So for a strong hydrogen bonding, electronegativity of the donor should be more and electronegativity of the acceptor should be less. Why is that? Let me explain with suitable examples. For hydrogen bond formation, both hydrogen bond donor and hydrogen bond acceptor must be present. And for a strong hydrogen bond, electronegativity of the donor should be higher and that of the acceptor should be lower. So these are the two major requirements for a strong hydrogen bond. Now let's see what happens when the electronegativity of the donor increases. Now when the donor's electron withdrawing power is greater, it tends to attract or pull the shared pair of electrons closer to its nucleus and thereby acquires a partial negative charge and leaving the hydrogen atom with a partial positive charge. So when the highly electronegative donor atom pulls the electron towards itself, the hydrogen atom will be more de-shielded. And greater will be the exposure and attraction of the proton of the hydrogen atom towards the acceptor atom with lone pair of electrons. So greater the electronegativity of the donor atom, more will be the de-shielding of the hydrogen atom. So for a strong hydrogen bond, electronegativity of the donor atom should be more. More the de-shielding of hydrogen, stronger will be the hydrogen bond. And this is about the electronegative donor atom. And what about the acceptor atom? What should be the electronegativity? Now the acceptor's electron donating ability is greater when the electronegativity of the acceptor is lower. So lower the electronegativity of the acceptor atom, the stronger will be the hydrogen bond, because when the electronegativity of the acceptor atom is less, its electron donating ability increases, resulting in a stronger hydrogen bond. Now here there are two different scenarios. The first scenario where you find hydrogen bond formation between same molecules, and second scenario where you find hydrogen bond formation between different molecules. So in case of hydrogen bond formation between same molecules, for a stronger hydrogen bond, that is the hydrogen bond strength is directly proportional to the electronegativity of the donor atom. And in case of hydrogen bond formation between different molecules, hydrogen bond strength is directly proportional to the electronegativity of donor atom and inversely proportional to the electronegativity of the acceptor atom. So here's a table depicting the electronegativity of four important elements that participates in hydrogen bonding. That is hydrogen, nitrogen, oxygen and fluorine. Where fluorine is the most electronegative element with value of 4 on the Pauling scale, and least electronegative is hydrogen atom with a value of 2.1. Now the donor order is fluorine greater than oxygen greater than nitrogen is in turn greater than carbon, which is a special case. And the acceptor order is nitrogen greater than oxygen, oxygen in turn greater than fluorine. Now let's consider this first scenario where you find hydrogen bonding between similar molecules. Now in case of hydrogen bonding between same molecules, the donor and the acceptor atom will be same. And one can arrange the order of strength of hydrogen bond based on the electronegativity order, with first preference given to fluorine followed by oxygen and nitrogen. And what about hydrogen bonding between different molecules? In case of hydrogen bonding between different molecules or two different molecules, the donor and acceptor atom will be different. In such cases, one can arrange the order of strength of hydrogen bond based on these three steps. The first step will be to group the molecules where the donor and acceptor are the same. So first group the molecules where you find hydrogen bonding, where both the donor and acceptor atoms are the same, and follow the electronegativity order in order to arrange them. And second step will be to find out hydrogen bonding between molecules where the electronegativity of the donor is more and the electronegativity of the acceptor is less. And least preference is given to the molecules engaged in hydrogen bonding where the electronegativity of the donor is less and the electronegativity of the acceptor is more. So the key takeaway is that for a strong hydrogen bond formation, electronegativity of the donor should be more and electronegativity of the acceptor should be less. Let me explain with multiple examples. So in the first scenario, we come across hydrogen bonding between similar molecules, where the strength of hydrogen bond decreases with decrease in the electronegativity of the donor atom. So here you find hydrogen bonding between similar molecules. We have three different cases: hydrogen bonding between hydrogen fluoride molecules, water molecules, and ammonia molecules. Of these three cases, hydrogen fluoride forms a very strong hydrogen bond. Why is that? Because the interaction between hydrogen fluoride molecules has a bond energy of 161.5 kilojoules per mole. So before I explain this particular concept, let me give you the meaning of bond energy. So what is bond energy? Now bond energy is a measure of the strength of the bond, or you can say it is a measure of the bond strength. That is, it is the energy required to break the hydrogen bond. And generally it is expressed in units of kilojoules per mole or kilocalories per mole. So here, what does this value signify? That is 161.5 kilojoules per mole. So this much amount of energy is required to break this particular hydrogen bond between the hydrogen fluoride molecules. And the bond energy for water molecules is 21, while in case of ammonia molecules, it is 13. You can see as the electronegativity of the donor atom decreases, the bond energy also decreases, which signifies that decrease in electronegativity decreases the bond energy. So the strength of hydrogen bond decreases with a decrease in the electronegativity of the donor atom. So in case of hydrogen bonding between similar molecules, always remember strength of hydrogen bond is directly proportional to the electronegativity of the donor atom. And the second scenario, where you find hydrogen bonding between different molecules, where the strength of hydrogen bond increases with a decrease in the electronegativity of the acceptor atom. So here you find three different interactions with different bond energy values. So you find interaction between hydrogen fluoride and ammonia molecules, water and ammonia, and interaction between water molecules. Now we considered the interaction between water molecules as a reference in order to gain insight about the importance of the electronegativity of the acceptor atom or its influence on hydrogen bonding. Now in case of hydrogen bonding between different molecules, the strength of hydrogen bond is directly proportional to the electronegativity of the donor atom and inversely proportional to the electronegativity of the acceptor atom. And that is why you find bond energy of 47 kilojoules per mole in case of interaction between hydrogen fluoride and ammonia molecule. Why the bond energy is greater or more in case of this particular interaction as compared to interaction between water and ammonia molecule? So in both the cases, you find that the electronegativity of the donor atom is more than the or it is greater than the acceptor atom. So how come the bond energy is more in case of hydrogen fluoride and ammonia interaction? The reason is the fluorine atom in hydrogen fluoride is a better donor because of its greater electronegativity as compared to water, I mean oxygen in water, whose electronegativity is less than that of fluorine. And the acceptor atom is same in both the cases. So it is nitrogen present in ammonia for both the cases. So nitrogen in ammonia is a better acceptor with a lower electronegativity. And now let's focus our attention on interaction between water molecules with a bond energy of 21 kilojoules per mole. I use this particular interaction in order to explain the importance of electronegativity of the acceptor atom. So nitrogen in ammonia is less electronegative as compared to the oxygen in case of water. And that is why it has lowest bond energy value. And therefore, this is the order you find. That is the strength of the hydrogen bond increases with a decrease in the electronegativity of the acceptor atom. Now, second factor is the polarity of the molecule. The polarity of the molecule impacts the strength of the hydrogen bond. Here you find interaction between polar water molecules and interaction between polar hydrogen fluoride molecules. So both are polar in nature. So polar water forms a strong hydrogen bond, while more polar hydrogen fluoride forms a very strong hydrogen bond. So bond energy in case of water molecules is 21, while in case of hydrogen fluoride molecules it's 161.5 kilojoules per mole. Why the bond energy in case of interaction between hydrogen fluoride molecules is greater than interaction between water molecules? The reason is hydrogen fluoride is more polar than water molecules. So in polar molecules, you'll always find that the partial positive charge on the hydrogen atom is more prominent, because in this particular interaction you find the hydrogen atom is covalently bonded to the electronegative fluorine atom. Because of the greater electronegativity of the fluorine atom, it tends to attract or pull the shared pair of electrons closer to itself, leaving the hydrogen atom with a partial positive charge. So making it more polar. So more polar the molecule, more favorable it is for hydrogen bond interaction, resulting in a strong hydrogen bond. And that is why interaction between hydrogen fluoride molecules is much stronger as compared to interaction between water molecules, because fluorine atom is more electronegative than oxygen atom, making hydrogen fluoride molecule more polar than water molecule. Now here's a special case where you find interaction between water molecule and methyl fluoride. Now both the molecules are polar in nature. So in case of water, it is a polar molecule with electronegative donor atom covalently bonded to a hydrogen atom. Well, in case of methyl fluoride, you will find that the fluorine atom is the acceptor atom with lone pair of electrons, covalently bonded to carbon atom, not to hydrogen atom. So methyl fluoride, it is a highly polar molecule because of the presence of the fluorine atom. So though the fluorine atom is not covalently bonded to hydrogen atom, it gives high polarity to the molecule, where fluorine atom is playing the role of a acceptor atom with lone pair of electrons. So here you may raise a question saying that how come fluorine being more electronegative than the donor oxygen atom results in a hydrogen bond formation. So this is a special case where fluorine being more electronegative than the donor oxygen atom. So the most important factor is the size of the atom. So fluorine atom is smaller in size, and this leads to increase in charge density, that is negative charge density, favoring the hydrogen bond formation, which will be the next factor that I will be discussing. So the key takeaway is the polarity of the molecule definitely impacts the strength of hydrogen bonding, and molecules with more pronounced dipoles create a stronger hydrogen bonds because the partial positive charge on the hydrogen becomes more prominent. Now the next factor is the size of the electronegative acceptor atom. Now the strength of the hydrogen bond also depends on the size of the electronegative acceptor atom with lone pair of electrons. Now let's focus our attention only on the size of the hydrogen bond acceptor. So for a stronger hydrogen bond formation, the separation between the acceptor and the electron deficient hydrogen should be less than or equal to 3 angstroms. And this is the size order of the electronegative acceptor atom. Fluorine is less than oxygen and oxygen is smaller in size as compared to nitrogen atom. So remember, this is the size order and not the electronegativity order. And here's a table depicting the atomic size, where you find the atomic radii of that particular element in picometers. And the atoms are arranged in the increasing order of their size, with fluorine being a small sized atom. With decrease in size of the atom, there is increase in the negative charge density, which is favorable for hydrogen bond formation. And with increase in size of the atom, there is decrease in the negative charge density, which is not favorable for hydrogen bond formation. And that is how the size of the acceptor atom plays a crucial role in deciding the strength of the hydrogen bond. Because the atom with smaller size has a increased negative charge density. Now the hydrogen bridge parameter is governed by the size of the acceptor atom. So what are the hydrogen bridge parameters? There are two major hydrogen bridge parameters. One is the separation between the hydrogen and the acceptor atom, that is the distance, and second is the bond energy. And the parameters of the hydrogen bridge can be utilized to accurately assess the strength of the bond. So the hydrogen bond strength generally decreases with increase in the size of the acceptor atom. So you can see that as the size of the atom, that is the acceptor atom, increases, now two things are happening with increase in the size of the acceptor atom. One is the distance between the proton on the acceptor atom is increasing, the separation increases, and the bond energy decreases. So with increase in the size of the acceptor atom, the distance increases, at the same time the bond energy decreases. Now in case of fluorine, oxygen and nitrogen atom, you find only two shells. So all these three atoms, they have only two shells with lone pairs of electrons, while in case of bigger sized or larger sized atom like chlorine, you find three shells. So as the size of the atom increases, the number of shells also increase. So in case of fluorine atom, the electronic configuration of fluorine is 1s to 2s to 2p5, and because of its small atomic size, the electron density increases, and thereby the crowding of electrons also increase, and thereby the small size of the fluorine atom increases the negative charge density, attracting a hydrogen atom and strengthening the hydrogen bond. So as the size of the atom increases, what happens? The electron density decreases and the crowding of electrons also decrease. So as the size of atom increases, like in case of oxygen and nitrogen, the negative charge density decreases, so making it insufficient to attract a hydrogen atom. And as a result, the distance between the hydrogen and the lone pair of electrons increases, leading to a decrease in hydrogen bond strength. So what about the chlorine atom? Why is that chlorine atom is not participating in hydrogen bonding? It is because of its bigger atomic size. So as I already mentioned, there are three shells in case of chlorine atom, and as a result, there is more space in the third energy level, which leads to less crowding and dispersal of electrons. And as an outcome, the large size of the chlorine atom results in a lower negative charge density, which is insufficient to attract a hydrogen atom. So despite its electronegativity, the chlorine atom size leads to electron density that is too low to form hydrogen bonds. And that is how the size of the atom plays a vital role in deciding the strength of the hydrogen bond. Another interesting factor which decides the strength of hydrogen bond is extensiveness, where you find hydrogen bonding in networks. So you'll find hydrogen bond formation with extensive networks, especially in case of water and biological macromolecules like protein and DNA, where the strength of hydrogen bond is influenced by the number of hydrogen bonds formed and their arrangement. And this leads to its unique properties like high boiling points in case of water and specific structural conformations in case of biological macromolecules like protein and DNA. So here I like to explain two examples where you find hydrogen bonding in extensive networks. The first example will be that of water. So water forms four hydrogen bonds in a tetrahedral structure, giving high its crystalline, less dense structure. So when you observe the structure of water molecule, you will find that the two hydrogen atoms are covalently bonded to electronegative oxygen atom with two lone pairs of electrons. And that is how water molecule forms four hydrogen bonds. That is, two hydrogen atoms contribute towards two hydrogen bonds, while two more hydrogen bonds are formed due to the two lone pairs of electrons on the electronegative oxygen atom. So we are all familiar with the genetic material DNA. So DNA is the genetic material present in the nucleus of human cell. It is 2 meters long when it is stretched out from end to end. It has two strands, 1 and 2, and these two strands are held together by multiple hydrogen bonds found between the complementary base pairs adenine and thymine, guanine and cytosine. So you'll find two hydrogen bonds found between adenine and thymine and three hydrogen bonds found between guanine and cytosine. Individual hydrogen bonds may be weaker, but multiple hydrogen bonds in extensive networks increases the cumulative strength of the bond and enhances the stability of the molecule. And therefore, the double helix DNA structure is highly stable because of multiple hydrogen bonds formed between the two strands of the double helix DNA structure. So the stability of the double helix DNA structure is due to multiple hydrogen bonds formed between the complementary base pairs adenine and thymine, guanine and cytosine. So what is the key takeaway? So the key takeaway is that individual hydrogen bonds may be weak, but the collective network increases the cumulative strength and enhances the stability. Moving on to the environmental factors. Now, environmental factors like temperature and solvent effects can also influence the strength of the hydrogen bond. So water freezes at 0 degrees Celsius. So water turns to ice as it freezes. And as the temperature increases, when the temperature is greater than 0 degrees Celsius, you can find a physical transformation from the solid to the liquid form. That is, as the temperature increases from, when it is greater than 0 degrees Celsius, you will find that the ice melts and there is a physical transformation from the solid to the liquid form. And when you heat the water, water boils at 100 degrees Celsius. As an end result, individual water molecules, they escape into vapor phase. So all this happens because of the temperature. At increased temperature, the thermal energy weakens the hydrogen bonds and disrupts the hydrogen bond interaction between the molecules and ultimately breaks the hydrogen bond. Now solvents also play a crucial role in affecting the strength of the hydrogen bond. Now polar solvents like water and alcohol, they stabilize the hydrogen bonds, while non-polar solvents like pentane, hexane and toluene, they disrupt the hydrogen bonds. Now alcohol is soluble in water and thereby it stabilizes by hydrogen bonds. while non-polar solvents like pentane, hexane, and toluene, they lack both donor as well as acceptor atoms, and thereby they disrupt hydrogen bonds. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in my next interesting tutoring session.